Hi, and welcome to this second basic introduction to GRASP. I hope you've already watched the first, where we used the wizard to set up a single offset reflector and perform the analysis to see the final radiation pattern. In this video, we'll also use the wizard, but now look at a dual reflector and pay more attention to some of the objects created, in particular the physical objects or PO objects. We'll also see how these play a fundamental role in the commands that perform the analysis. We start the wizard to design a dual reflector of the Gregorian type intended for Ku-band coverage from a geostationary satellite. We aim at a configuration with the main dish at the side of the spacecraft, while the feed and subreflector are on the Earth deck. We start at the low end of the Ku-band, 10.95 GHz, a main reflector diameter of 1.5 meter, fairly flat with an f/d ratio of 1.25. To change from the default Cassegrain, we set the eccentricity of the sub to a number smaller than 1, we set it to 0.3, to get an ellipsoidal subreflector, which characterizes the Gregorian type antenna. With the final configuration on the spacecraft in mind, we move the subreflector and the feed closer together by reducing the distance between the two focal points of the ellipsoidal subreflector and set this to 0.2. To make the design offset, we can grab the feed and move it carefully, or we can enter the value of the angle between the main and the subreflector axis. 7 degrees, for example, would not be sufficient, while 20 degrees may be too much. For now, the most important thing is to create a design which offers a blockage-free design, so we select 12 degrees. We ask the wizard to generate objects for us, and we're in principle ready to perform the analysis. But before doing so, I want to inspect some of the objects in more detail. GRASP uses physical optics to calculate the reflected field from any reflector. PO is based on the concept of induced currents on the surface, supplemented by a high-order correction term called PTD currents along the edge of the reflector. Objects of the class PO analysis specifies this in more detail. Here you can see a PO object that points first to the frequency object of interest and then to the scatterer of interest, in this case the main reflector. The next entries specify which method to be used, PO plus PTD, or only one of those two, in case you want to do some special investigations. I now click the Show Advanced Settings that reveals further attributes of the PO analysis object, in particular the number of PO points. This is the density of a grid placed on the surface in which the currents are computed. The number of points depend on whether we are computing near fields or far fields, and if we're close to or far away from the bore side of the reflector. There are good rules of thumb for these numbers in the manual, but to make it easier for you, we have added an iterative procedure that determines the necessary points for a given scenario. I'll get back to this when we do the analysis. For now, I just want to point out that it's possible to set the numbers manually here, so if you have run the iterative procedure once for a complicated antenna system, you may save time in succeeding analyses by taking the numbers found and enter here. We now take a look at the commands in the Command tab. There are 4 in total. The first one deals with the PO object for the subreflector and the feed. When executing this command, GRASP will calculate the induced currents on the subreflector caused by the feed. The next one uses these currents as source for calculating induced currents on the main reflector. In other words, this specifies how the sub illuminates the main reflector. Note that there are arguments to these commands. One of the arguments specifies auto-convergence of PO to be on, which initiates the iterative process of finding the right grid size for computing the currents on the subreflector. It also specifies that we need to have enough current elements that the field from these has converged both on the main reflector and in the far field. The main reflector PO only needs to be converged in the far field, since this is where we will evaluate that field contribution. The third command is of the type GetField, which performs the numerical integration of the currents on the main reflector in the directions in space specified by the dual cut object. This is the dominant contribution to the main beam direction from this antenna system. However, the feed and the sub will also radiate in the far field, and as always in physical optics, we need to add all the contributions to get the most accurate results. This is what happens in the fourth and final command. We execute the commands and it finishes in a few seconds. The screen output lists the 4 tasks, and I want to point out the obtained values of the PO points, PO1 and PO2, and the number of PTD points as found from the iterative procedure. Finally, we're ready to see the radiation pattern from this antenna calculated over the region suggested by the wizard. But before you go, I want to show you some interesting results for a wider pattern. I go back to the Antennas and Scatterers tab and select the field storage object dual cut. It specifies a theta range of plus minus 5.2 degrees. I can change this to plus minus 50 degrees. And if I increase the range, I should also increase the number of samples to get a smooth pattern. So I also adjust this by a factor of 10. It now takes slightly longer, and the values of the PO currents are increased to give us the pattern we will see here. Note the high side lobes in the cut taken in the plane of offset. This is caused by the feed spillover past the subreflector and is adequately accounted for with the PO procedure. Thank you for watching this video on how to set up a dual reflector antenna analysis in GRASP. I hope you enjoyed it.